Okay, I wanted to very quickly derive the expression for the gravitational potential energy from the expression that we have here for the gravitational force, using what we know about conservative forces and how to get the potential energy from the conservative force, like we've been doing in our energy unit. So if you remember, we know in general that the potential energy as a function of x is negative the integral of the conservative force as a function of x dx. Now, our variable in the situation is r, not x, but that doesn't matter. All we have to do is change all the x's out to r's. So we would be deriving u of r is negative the integral fc of r dr. Now, you'll notice that negative, remember, is because the potential energy changes opposite the work done by the conservative force. So if I move this little mass further away from the Earth or from the planet, it will increase in potential energy if I move it that way, and it should decrease in potential energy if I move it that way. As I move it to the right, the conservative force, which is shown by the big red arrow, will do negative work. As I move it to the left, the conservative force will do positive work. Now, we also remember that, we want this to be such that when I move the mass, the little mass, higher away from the Earth, when I move it in this direction over here, I should increase the potential energy of the system. And so that's the intuition we want to keep in mind. Okay, so here's a little problem. We know when we're going to use this formalism up here, we also need to have some representation of u at a particular value so we could figure out what the constant that comes out of this integral is. Now, in general, we've done like u of 0, for example. But I've told you like u of 5 equals this, or u of something equals this. The problem here is that we don't really have a good place. Like you can't get to r equals 0 very easily, right? Because that's at the center of the Earth. So that would be kind of a weird place to talk about. The potential energy being 0. And we'll see that the force actually changes when you get inside the Earth. So that's going to be something different as well. So we need to think of a good place to think about the potential energy function. And you might say, well, what if I put the little red mass on the surface of the planet? And that might seem like a good idea. You could certainly do that. But if there's multiple planets and we're looking at like the potential energy overall of that little red mass in relation to those other three, then whose surface do we use, right? That's a big paradox. And so instead what you want to do is you want to think, what is the one place in the universe that everything has in common? And the answer is infinity. And so even though it seems kind of weird, we're going to make our boundary condition, we're going to define our 0 of potential energy to be u at r equals infinity equals 0. Now that's weird, right? Because I just said if I move these masses really far apart, the potential energy should increase. But if you think about it a little bit, what that means is that if 0 is when the masses are infinitely far apart, then anything before that is negative. So if I still move my little mass out in this direction, it's going to 0, but my potential energy is increasing because everything else is negative. There's something conceptually very attractive about that because it means you kind of think of being in a hole, like having negative potential energy, and you need to gain energy to escape from the Earth's gravity. So that's a really good way to think about it. All right, so u of infinity we're defining as 0, and u of r is negative fc of r dr. So let's slap on our integral. We're going to have a ton of negative signs. U of r is negative the integral, and the force, remember, is negative gmm over r squared dr. So those two negatives are going to go away. And now we can pull the constants out. So u of r equals gmm the integral of r to the negative 2 dr. And now you may, if you've taken calculus, you've seen this integral many times. If you haven't, you might say, do I treat this the same way I treat positive powers? The answer is yes. As long as the power isn't -1, you could treat it the same way. And so we add 1 to the power and then divide by the new power. -2 plus 1 is -1. So we divide by -1, and I get u of r equals gmm over r with a negative sign out front from that integral plus any constant. And then I say, well, u at r equals infinity is negative gmm over infinity plus c. Well, this I know is 0 in the limit that r goes to infinity. And so since u of infinity I'm defining as 0, that tells me c is conveniently 0. And so my expression for the potential energy as a function of r, which you may remember from last year, is negative gmm over r. Gravitational potential energy is a function of r with u at infinity equal to 0. So let's graph that out. Let's take a look for a minute. I'm going to go to a new page. I have u of r is equal to negative gmm over r, and I want to plot that as a function of r. Well, we know as r approaches infinity, this approaches 0, but then and we know as r approaches 0, this inside will get very, very big, but negatively big. So my graph looks like an inverse 1 over r graph. And what we see is, even though it's a little strange, since we've defined the 0, u of infinity equals 0, for small r, meaning when I'm close to the planet, I have a deeply negative potential energy. And as I move further away from the planet, u of r increases. And it's weird because it's negative increasing to 0, but that's still increasing. So our intuition, which was that as we moved further away from the planet, if here was our planet M and here was our little mass M, as I moved further that way, my u of r should increase, and it does because it's very negative and it approaches 0. So just to summarize, u of r is negative gmm over r. That's derived from the conservative force. F of r is negative gmm over r squared. And if you want to check it, I won't do it here, but we also know that u d by dr of u of r negative, the derivative of the potential energy should give us back the force. And if you check that out with these two functions, you'll see that we did a good job. All right, so I think what I wanted to say was, I think that's it. That's all I have to say. So the book does it a little differently. I think this is a little simpler. So watch this, then you can skim through the reading. This is going to let us do a lot of cool things. I do have something else to say. The one other thing I wanted to say was, let's look at an example real quick. The example I want to look at is something in circular orbit. So let's say we have the Earth, or any planet mass m, and we have a little guy orbiting it in a circular orbit that's supposed to be circular. I'm not doing a great job of circular, but at some radius r, and it's a little mass m. So that's going around, and we know a few things about this, right? We know from centripetal force that the centripetal force, mv squared over r, is supplied by the magnitude of the gravitational force. And if I do a little bit of algebra there, I get that v for a circular orbit, which is in your reading, equals the square root of g mass of the planet over r. Notice the little mass is canceled, one of the r's canceled, and that's what I get. So that's cool. What is the total energy of this little mass orbiting at velocity v look like? Well, we have an expression right here. We can calculate its kinetic energy. That's 1/2 mv squared. Well, v squared is just g m over r. And then we know its potential energy is negative g m over r. And if we look at this, it's kind of cool. We have this negative gmm over r. I can multiply top and bottom by 2. I can add it to this, and it tells me that in a circular orbit, the energy, and this is only true in a circular orbit, is equal to negative gmm over 2r. And what this tells you is that you could think of something in a circular orbit since it has a negative total energy. Note the kinetic energy was still positive. It was the negativeness of the potential energy that outweighed it, that it's a bound orbit. It has a positive total energy. So this is really cool. So we have a few things now. We also reviewed the, oh, that wasn't a nice highlight color at all. I don't like that. That was too depressing. Let's go to yellow. So you have the velocity of, if you're in a circular orbit, we had our gravitational potential energy equation. We could actually just make our kinetic energy equation using that V, and when we add it all up, we wound up with this. So that's really neat. We'll talk more about this and we'll analyze orbits a little bit more on Tuesday, but I wanted to give you a little preview of how we derive all of these equations. So just a final summary. We have the gravitational force is negative gmm over r squared. U of r is negative gmm over r. And then we also know that E total in a circle, but only in a circle, is given by negative gmm over 2r. All right, thanks for watching.